Hello students, so in this lecture we shall discuss about angular momentum. And it's used in spherical harmonics. Now, we know that the z component of angular momentum is equal to minus h cross 10 pi delta phi, where as spherical harmonics means we are representation in terms of r, theta and phi. That means we take the x, y, z coordinates. This is r, this is theta, and this is phi. So that's how the point P here is r. Sorry. This is r, theta and phi. So this is how the z component of the angular momentum is written. And we also know that L square is equal to x square plus Ly square plus Lz square. And we can write L squared in terms of the spherical harmonics as L squared is equal to minus h cross square 1 by sine theta del by del theta of sine theta del by del theta plus 1 by sine squared theta del square by del phi square. And you can write L square, a function of only theta and phi, as equal to lambda h cross square phi. Just set it in different color. Where this value lambda h squared is represents the eigenvalues of the operator L square, the operator sign L square. Now this lambda value, this takes L into L plus 1 values, where L starts from 0 to 1, 2, 3, dot dot dot. And for each value of L, there are 2L plus 1 fold degeneracy. That is 2L plus 1. It actually means, it implies that 2L plus 1 eigenfunction corresponding to the same eigenvalue. Which is L into L plus 1 H cross square. These eigenfunctions, these degenerates having degeneracy, these are actually called the spherical harmonics. And are denoted by y, ln, theta, and phi. So obviously we can write L square y ln theta phi equal to L into L plus 1 H cross square y ln theta phi. Where L again is from 0 to 1 to 3 and M stands from minus L to plus L. Now these spherical harmonics, these y ln theta phi, they are actually simultaneous eigenfunctions of Lz and L². So we can write Lz y ln theta phi is equal to m h cross y ln theta phi. This is your m h cross. Now, in classical mechanics, angular momentum L is represented as the R cross P, cross product of position momentum vector. So we can write Lx, as equal to ypz minus zpy, and in term is equal to minus h cross y del by del z minus z del by del y, and similarly we can write Ly as equal to ZEX minus XEZ, and LZ is equal to XEY minus YEX. In order to determine the eigenvalues and eigenfunctions of the operator L square, we can express x, Lx, Ly, and Lz in terms of spherical polar coordinates. So these all are in Cartesian polar coordinates. This is in Cartesian. This has to be converted into spherical polar coordinates. That means in terms of r, theta, and phi, and so it actually, if we draw the diagram, that means of the position coordinates, Cartesian to spherical polar coordinates, this is r, this is theta, and this is phi. So we can write the following equations. We can write x is equal to r sin theta cos phi. I can write phi is equal to r theta sin phi. And we can write z is equal to r cos theta. Another identity is r square is equal to x square plus y square plus z square, and tan square theta is equal to x square plus y square plus z square, and lastly we can write tan phi is equal to yx. So taking all these equations, we finally arrive at the representation of Lx, Ly, and Lz in terms of spherical polar coordinates. So we can write, we get the following equations. We get Lx equal to h cross sin phi del by del theta plus cot phi cot theta cos phi del by del theta del by del phi, and we get Ly is equal to h cross minus cos phi del by del theta plus cot phi sin phi del by del phi. And we have previously said that this Lz is equal to h cross minus h square by del phi. And so you can write, so Lz is equal to minus h cross del y del phi, and so Lz square is equal to minus h cross square del square by del phi square. And so if we take all the values of L, we know that L square is equal to Lx square plus Ly square plus Lz square. So if we take the square of this Lx, Ly and Lz square and we add it up, so ultimately we get L square is equal to minus h cross square del square minus 1 by r square del by del r r square del by del r.